We now start the discussion on module 2 of chapter 8. Now, in this module, we are going to see what is the motivation behind introducing the fundamental theorem of integral calculus for Lebesgue integration. So, what we are going to do is that we are going to recall the form of fundamental theorem of integral calculus for Riemann integration and try to understand what is its deficiency, and for that we will have to present a very tough example which will take a lot of time to understand. So, with this we go to our first slide, but before we go to that tough example, we will see a property of Lebesgue integrable functions which we will need later in the last module of this chapter. Now, for that let us again recall the definition of absolutely continuous function. So, the definition is that a function f is said to be absolutely continuous on closed interval a b if for any epsilon greater than 0 there is a delta greater than 0 such that sigma I equal to 1 to n mod f di minus f ci is less than epsilon whenever we take a finite collection of non-overlapping intervals closed ci di 1 less or equal to I less or equal to n in closed interval a b with the property that the sum of the lengths of these intervals is less than delta. Now, we come to our result. If f is Lebesgue integrable on closed interval a b, then the function capital F defined by capital F x equal to integral a to x f d mu is an absolutely continuous function on closed interval a b. So, by our assumption f is Lebesgue integrable on closed interval a b, and this means that integral a to b mod f d mu is equal to say a number alpha which is finite. Recall that we had said that f is Lebesgue integrable if and only if mod f is also so. For epsilon greater than 0, then we can find a delta greater than 0 such that for every set A subset of closed interval a b whose measure is less than delta, we have integral over a mod f d mu less than epsilon. So, this follows from the last result of the module 1 of chapter 8. Now, let closed ci di where 1 is less or equal to I less or equal to n is a collection of non-overlapping intervals in closed interval a b with the sum of their lengths less than delta. Write the union of these intervals as the set capital A. Then we get sigma I equal to 1 to n mod capital F d I minus capital F c I. This is equal to sigma I equal to 1 to n mod integral Ci to di f d mu, and this is again less or equal to sigma I equal to 1 to n integral Ci to di mod f d mu, because we know that for any Lebesgue integrable function f, mod integral f is less or equal to integral mod f, and this is less or equal to integral over a mod f d mu, and this is again less than epsilon, and this shows that the function is absolutely continuous. Now, we start with the fundamental theorem of integral calculus, the version which you know for Riemann integrable functions. The version that you are aware of is that if a bounded function f is differentiable on closed interval a b and the derivative f dash is Riemann integrable on closed interval a b, then integral a to x f dash t dt is equal to f x minus f a for every x belonging to closed interval a b, and in particular we get integral a to b f dash t dt equal to f b minus f a, which we use to calculate the values of definite integrals. Now, here the main point is that the derivative is Riemann integrable. This condition is essential for this theorem. In calculus courses, you have come across functions which have unbounded derivatives. So, for these functions this theorem is not valid, and even there are functions whose derivatives are bounded, but still the functions are not Riemann integrable. The example is not at all easy, as I have said. So, let us start to construct the example. In any closed interval a b, consider the function g x equal to x minus a whole square sin 1 by x minus a if a is less than x, less or equal to b, and g x takes the value 0 at the point x equal to a. Now, it is easy to see that g dash a equal to 0, and at all other points in closed interval a b, g dash x is equal to 2 into x minus a sin 1 by x minus a minus cos 1 by x minus a. You can calculate it. As x approaches the point a, see that there are infinitely many branches of the curve g dash, and g dash is equal to 0 at infinitely many points. Further, whenever we take the points a plus 1 by n pi for any positive integer n, we get g dash x equal to 1. So, this shows that g dash is not continuous at the point a. Now, let us choose a point C in the open interval a to a plus b by 2, where g dash c is equal to 0, because as we have said there are infinitely many points where the derivative is equal to 0. Choose a point D belonging to the open interval a plus b by 2 and the point B such that the difference C minus A is equal to B minus D. And we have C minus A whole square sin 1 by C minus A is equal to minus D minus B whole square sin 1 by D minus B. Now, define a function h on closed interval a b in this way. H takes the value 0 at the end points a and b. For all points x in the open a c closed, h x takes the value x minus a whole square sin 1 by x minus a. In the open interval c d, h x takes the constant value c minus a whole square sin 1 by c minus a, and in the part d less or equal to x less than b, h x takes the value minus x minus b whole square sin 1 by x minus b. We can observe that the derivative of this function h exists at each point of closed interval a b, and further the derivative is bounded in closed interval a b, though the derivative is not continuous at either of the end points a or b. And moreover, mod h dash x is less or equal to mod x minus a whole square and mod x minus b whole square for all x belonging to closed interval a b. Now, let us choose a perfect nowhere dense subset E of closed interval 0 1 containing both the endpoints 0 1, which has positive Lebesgue measure, that is we have mu e greater than 0. See that closed interval 0 1 minus e can be written as countable union of open intervals. So, say we can express the set in this form: union k equal to 1 to infinity open interval a k b k, and for each interval closed a k b k, let f k be the function h that we have defined on closed interval a b. So, for each k on closed interval a k b k, we take the same function h defined on closed interval a k b k. Finally, we define our desired function f from closed interval 0 1 to r in this way: f x equal to f k x if x belongs to open interval a k b k, and at all points in the complement, that is at all points belonging to the set E, f x takes the value 0. Observe that by our property of the function h, the function f is differentiable at each point of each open interval open a k b k, and so it is differentiable at each point of closed interval 0 1 minus e. Let us take an arbitrary point C from the set E. We have to show that f is also differentiable at the point C. So, in order to show that f is differentiable at the point C, we need to show that both the right and left hand derivatives at the point C exist and are equal. We will show only one case. So, let us consider limit x tends to c plus f x minus f c by x minus c, that is the right hand derivative. We will show that the right hand derivative is equal to 0. Similarly, we will be able to show that the left hand derivative is also equal to 0. So, that f is differentiable at the point C. Why? To see this, let epsilon greater than 0 be given, and let us take a point x from the open interval C, C plus epsilon. If x belongs to E, then there is nothing to prove. So, suppose that x belongs to open interval a k b k for some k belonging to capital N, because if x belongs to E, then by our definition the function takes the value 0 at the point E, and we do not have anything to prove. Otherwise, if we take a point from the complement of E, since the complement is the union of the intervals a k b k, so the point x must belong to at least one of the interval a k b k. Now, we observe that mod f x minus f c by x minus c, this is less or equal to mod f k x by x minus a k. This is again less or equal to mod x minus a k whole square by mod x minus a k, because recall that we had said that the function g dash is bounded by mod x minus a whole square as well as x minus b whole square. So, the right hand side, the quotient is equal to mod x minus a k, and this is less than epsilon. This shows that f dash c is equal to 0. And obviously, from the definition f dash is bounded on closed interval 0 1. So, we have an example of a function f on closed interval 0 1, which has bounded derivative at all points in closed interval 0 1. Now, we are going to show that the derivative f dash is not Riemann integrable in closed interval 0 1. How we observe this? So, let us recall the Lebesgue criteria for Riemann integrability, where we get the result that a bounded function f defined on closed interval a b is Riemann integrable on closed interval a b if and only if f is continuous almost everywhere on closed interval a b, that is, in other words, the set of all discontinuities of the function f has Lebesgue measure 0. So, we will use this criteria to show that f dash is not Riemann integrable. So, in other words, we will show that the set of discontinuities of f has positive Lebesgue measure. See that f is discontinuous at each point of E, and which will consequently show that f cannot be continuous almost everywhere, as the set E was chosen in such a way that it has positive Lebesgue measure. So, let us show that f is discontinuous at each point of E. So, we start with an arbitrary point C from the set E. By our assumption, the set was chosen in such a way that E is perfect and nowhere dense, and so every point of E is a limit point of E, since it is perfect. And so, we can find a subsequence a k n, n belonging to capital N, that is convergent to the point C. For each positive integer n, let us choose another positive integer q n greater than n, for which mod f dash x n is actually equal to f k dash x n, and this is equal to 1 when x n is chosen as the point a k n plus 1 by q n pi. Observe that the sequence x n is convergent to C, because the sequence a k n is already convergent to the point C, and 1 by q n pi tends to 0 as n tends to infinity, and consequently the image sequence, if we consider f dash x n, this is not convergent to f dash c equal to 0, and this shows that f dash is not continuous at the point C. So, to summarize, what we did in this module is that mainly we have recalled the version of fundamental theorem of integral calculus for Riemann integration, where the Riemann integrability of the derivative is essential, and we have shown by an example that we cannot drop this condition and still get the result. In the next module, we are going to show that the fundamental theorem of integral calculus has a much better version for Lebesgue integration, in the sense that we do not need the assumption of integrability of the derivative to get the fundamental theorem. And with this comment, we end this module.